Tycho Brahe and Johannes Kepler are two titans of astronomy whose collaboration in the early 17th century paved the way for modern celestial mechanics. Both men, born in the late 16th century, brought unique skills and perspectives to the field, which when combined led to groundbreaking discoveries about the universe. Brahe's meticulous observations and Kepler's mathematical prowess formed a symbiotic relationship that fundamentally altered our understanding of the cosmos. Brahe, a Danish nobleman, was renowned for his accurate and comprehensive astronomical data, which he collected without the aid of a telescope, a tool that would only come into regular use after his death. On the other hand, Johannes Kepler, a German mathematician, sought to understand the underlying principles that governed the heavens, driven by a deep spiritual and scientific curiosity about the order of the universe. Their collaboration began under less than ideal circumstances, with Kepler initially working as Brahe's assistant. Despite their differences in temperament and approach, their partnership was ultimately a fruitful one, combining Brahe's detailed observations with Kepler's theoretical insights. This partnership, though sometimes strained, stands as a testament to the power of collaborative scientific endeavor. The significance of Brahe and Kepler in the history of astronomy cannot be overstated. Their work not only challenged existing beliefs about the universe, but also laid the foundation for future generations of astronomers, including Sir Isaac Newton. Through their efforts, they transformed the study of the heavens from a primarily observational science to one driven by mathematical and physical principles.
Tycho Brahe was born in 1546 in Denmark. From an early age, I was fascinated by the stars, an interest that was ignited by witnessing a solar eclipse at age 14. This defining moment led me to devote my life to astronomy. Over the years, I built the best observatory in Europe at the time and developed instruments that could measure the positions of celestial bodies with unprecedented accuracy.
Johannes Kepler was born in 1571 in Germany, and I displayed an innate talent for mathematics from a young age. My early work, Mysterium Cosmographicum, proposed that the distance of the planets from the Sun could be explained by the 5 Platonic solids, encapsulated within one another. This model, though incorrect, highlighted my innovative approach to understanding the universe.
Brahe's contributions to astronomy were monumental, particularly his comprehensive record-keeping. His detailed observations of the planets and stars over many years provided the most accurate data available at the time. These observations included a meticulous study of the 1572 supernova, which challenged the Aristotelian belief in the unchangeability of the stars, and his careful tracking of the 1588 Great Comet, which refuted the notion that comets were mere atmospheric phenomena.
Kepler's work, on the other hand, was characterized by his relentless pursuit of a mathematical harmony in the heavens. His ability to abstract and generalize from Brahe's data would eventually lead him to formulate the laws of planetary motion, fundamentally changing the way astronomers viewed the universe. His work exemplified the shift from qualitative to quantitative descriptions in science.
Before the collaborative efforts of Tycho Brahe and Johannes Kepler, the understanding of planetary motion was fraught with misconceptions and incomplete theories. The dominant astronomical model of the time, the Ptolemaic system, placed Earth at the center of the universe with planets moving in perfect circular orbits. This geocentric model was deeply intertwined with the philosophical and religious doctrines of the era, making any challenge to it both a scientific and a theological controversy.
Alternative models, such as the heliocentric theory proposed by Copernicus, which suggested that the Sun was at the center of the universe, faced significant skepticism and opposition. This model simplified some astronomical calculations but still relied on circular orbits, which could not accurately explain the observed planetary movements. The lack of precision in these models left many questions unanswered and called for a more robust framework that could reconcile observed phenomena with theoretical predictions.
The primary challenge was the inability of existing theories to predict planetary positions accurately. Astronomers had to rely on complex systems of epicycles, circles within circles, to describe the orbits, which were both mathematically cumbersome and conceptually unsatisfactory. These inaccuracies and the cumbersome nature of the Ptolemaic and Copernican systems highlighted the need for a new approach that could provide a more accurate and elegant explanation of celestial mechanics. Kepler himself initially struggled with these inherited complexities. His early work tried to fit planetary orbits into perfect geometric shapes such as circles and ovals. However, the precise data he inherited from Brahe eventually led him to abandon these idealized notions in favor of elliptical orbits, which provided a simpler and more accurate description of planetary paths. This shift was not just a technical improvement, but a fundamental change in the way celestial dynamics were understood. Section 4. Collaboration and development of laws. The collaboration between Tycho Brahe and Johannes Kepler was initiated when Kepler was appointed as Brahe's assistant in Prague in 1600. This partnership, though marked by occasional personal and professional tensions, was built on a mutual respect for each other's skills and contributions. Brahe possessed perhaps the most comprehensive astronomical data of the era, while Kepler had the mathematical expertise necessary to analyze and interpret these data. Kepler's analysis of Brahe's observations led him to conclude that planetary orbits were not circular but elliptical, a revolutionary idea at the time. This insight was the first of Kepler's 3 laws of planetary motion, which collectively describe how planets move around the Sun. The second law, which states that a line segment joining a planet and the Sun sweeps out equal areas during equal intervals of time, further demonstrated the variable speeds at which planets travel along their orbits. The third law, which shows a precise mathematical relationship between the square of a planet's orbital period and the cube of the semi-major axis of its orbit, provided a unified theory that applied to all known planets. These laws were radical not only because they contradicted the prevailing wisdom of circular orbits and uniform motion, but also because they applied a mathematical framework to physical astronomy, thus bridging the gap between theoretical mathematics and observational astronomy. The significance of each law cannot be overstated. The first law debunked the long-held belief in circular orbits, the second introduced the concept of aerial velocity, and the third established a harmonious relationship across all planetary motions. Together, these laws not only explained the complexities of planetary motion, but also provided the tools necessary for future astronomers to predict celestial events with great precision. Section 5. Revolutionary impact. The laws of planetary motion, formulated by Johannes Kepler, based on the meticulous observations of Tycho Brahe, marked a turning point in the history of astronomy. Their work laid the groundwork for the development of classical mechanics by Sir Isaac Newton and others, fundamentally changing our understanding of the universe. The impact of these laws extended beyond the realm of astronomy, influencing various scientific disciplines and contributing to the broader scientific revolution of the 17th century. Future astronomers were able to use Kepler's laws to make more accurate predictions of planetary positions, which was essential for navigation, calendar reform, and the eventual understanding of gravity. The precision of Kepler's laws also provided one of the empirical foundations for Newton's law of universal gravitation, linking the motion of celestial bodies with the physics of motion on Earth. Moreover, the acceptance of Kepler's laws helped to solidify the heliocentric model of the solar system proposed by Copernicus, which had initially met with resistance. This paradigm shift was not just scientific but also philosophical, altering humanity's place in the cosmos from a central position to one of many planets orbiting the Sun. The philosophical implications of this shift were profound, influencing everything from theology to human self-perception. In conclusion, the collaborative efforts of Brahe and Kepler did not just revolutionize our understanding of the cosmos, they also exemplified the transformative power of combining empirical data with theoretical insight. Their partnership underscores the importance of interdisciplinary cooperation in achieving scientific breakthroughs, a principle that remains relevant in today's complex scientific landscape.